Welcome to Chadev. All right. Let's thank our sponsor for the week. It's Code Science again. So yay for pizza. Today we have Will Wade speaking on systems thinkings, right? And we are also doing a raffle today for a JetBrains license, which I think you can use for IntelliJ, RubyMine, any of their products. So if you are interested, there's a sign-up sheet in the back, and you should go sign up because we're gonna do a random number generator at the end to pick the winner. So go sign up. Next week we have Rob Scott talking on Kubernetes. That should be pretty interesting. Please be sure to sign up on the meetup. The sooner you can do that, the better, because then we get a better head count for pizza and all of that. And do we have any community announcements? I know there's Hack Night next Wednesday with interview questions. So if you're interested in coming and practicing interview questions, come on and hang out. No, it is run by Lyndon from Carbon 5 and me from Zillion. Yay! Cool. And with that, let's welcome Will.
All right. All right, so as Anna mentioned, I'm Will Wade. You may know me better if I put my hat on. Oh, that Will Wade, yeah. So thank you all so much for coming out. I'm a developer at Carbon 5. If you don't know Carbon 5, we're a consultancy. We have an office here in town. We also have offices in SF, LA, and New York. And one of the things that Carbon 5 is well known for is our Agile practices. And so a lot of people come to us specifically because we have this reputation for being really good at Agile practices and applying them pragmatically in all the different client companies that we work with. But I'm here to say that Agile is not enough. I'm going to slash my company and say that I think there's a big piece that we've been doing but we haven't been talking about. And that is systems. So systems are all around us, and we teach our kids about them. This is a book from Disney in the late 1970s, and you have here, we've got like drainage systems, we've got plumbing, we've got electrical systems. We love to talk about all these systems with our kids. We teach them about the natural systems, the ecological systems, right? We have the water cycle, we have how all these things work together. And we even love, and I think this is probably one of the most interesting things, we love imaginary systems. We make up systems just for fun, and we love to go into amazing detail about these systems, whether they be mechanical or social or political, all these systems around us. And it's important to be able to understand how these systems work, both for just life and enjoying, I think, life around us, but also in our work as we're developing software. This understanding of systems will help us to see a bigger picture and avoid some mistakes. But systems aren't just around us. They're nested all the way down. So you have systems within systems within systems, which makes systems a little bit hard to think about, a little bit hard to understand at a large level, and we're going to be working at a pretty large level today. So the idea of this is to not necessarily get into all the minutiae of systems, but to give you some idea of how systems work so that you can start recognizing them around you. And of course, before we can start talking about something, we have to talk about the language we're going to talk about. And with systems, there is a ton of language. There are words out the wazoo. We've got macro systems, cybernetics, sub-optimization, lots of fun words, and we're going to try to get rid of as many of these as possible. And we'll touch on some of them. But you should know that like there's words around some of these concepts that are what we're going to be talking about, and there's words that go with them. So at the end, we'll have some resources, and you'll be able to be like, oh, that's the word for that thing. And that's no problem. But we're going to define systems today by this: a structure of things connected by relationships that produce behaviors. And these three pieces, the things and relationships and behaviors, are each key. Because you can have, right, this is from my living room floor. I have 3 kids. Very dangerous floor. And, it's called the Lego system, but I'm here to tell you it's not a system. These pieces, although they have the potential for relationships, right? They have all these potential relationships. As individual pieces, without those relationships, there is no system yet. It is merely sitting there waiting for someone to come along and create a system that will produce beautiful behaviors of spaceships and houses and I don't know, what all the other stuff my kids make out of Lego that I'm like, that's cool, whatever it is. But there are some other fun things that are some pretty simple systems that we can talk about. And from Russia, we should talk about Tetris. This is my wife's favorite game. And pretty much everybody has played Tetris. But just in case you haven't, this is the basic flow, right? There are new blocks that fall from the sky, and they fall onto other fallen blocks. And then if you clear a row, if you finish a horizontal row, you clear it out, and the height of the fallen blocks drops by 1. And we can kind of expand upon this system. This will be a recurring theme of where you start with this kind of basic concept, and you kind of fill it in a little bit, and fill it in a little bit more. And so we can go on and think about new blocks as the falling speed, right? How many new blocks you get, the falling speed affects the height of the fallen blocks. And how well you place those blocks determines how many rows you clear. And we can expand out a little bit further. Let's say, the falling speed actually tells you how much time you get per block. How much time you get per block affects your placement quality. The height of the falling blocks also changes how much time you get per block, right? And you have this idea, too, of next block knowledge. Maybe you can use the next block, but if the stuff's falling too fast, maybe you're looking at the next block, and that maybe negatively impacts your placement quality, meaning you clear less rows, meaning in the end, right, you lose the game. So here's a kind of a timeline view of the game. As you start, we have the black line, that's the height of the fallen blocks, and you can see over time the speed of the falling blocks, that bluish line. That's the levels, right? We have levels to the game. Eventually, we level up. And you might look closely at this and see your own game there, because around the middle here, there's kind of this turning point in the system where you're out of luck. You're going to lose the game at that point. Like after that point, you're no longer clearing enough rows, and the game's just going to go over. So all this builds up. We're slowly building up this language around systems. But one of the keys between Tetris and a lot of the systems we see around us is that the systems we see around us are nonlinear. So in the case of nonlinear, right, it's the classic question, the chicken or the egg, which came first? And if you're a chicken plant, you don't really care which came first. You just care that you're getting more chickens out of the eggs. And there are, again, some small systems we can see, a more cyclical view of the world. And a famous one is Conway's Game of Life. So if you aren't familiar with Conway's Game of Life, it is a grid of these squares, and each square is either black or white, which we could think of as dead or alive. And these squares, you have a starting situation, but then you apply some simple rules. So we have 4 rules. If a square is alive and it has 2 or 3 neighbors, it gets to stay alive for the next cycle. If it doesn't have enough neighboring squares, then it's going to die. Or if it has too many, it gets crowded out. And a dead cell, an empty cell, will become alive if it has 3 neighbors. And these 4 rules, we have these simple blocks, right? 4 simple relationships, let's say, and it produces an amazing variety of behaviors. And there's names for a lot of these behaviors. We have glider guns, and we have, I don't actually know what this one's called. We got all these kind of behaviors, and you can come up with new behaviors just by having a new starting set. Some of them will continue forever, and some of them will die out. Some of them have no known end. So we have this this cycle. And although we have a starting case, right, it's kind of like a lot of things in life, right? It's just happening over and over again, just like it might be in your Agile software development, right? And when we talk about Agile, I'm using it in the general sense, right? The concepts that change is good, that small steps are important, that feedback loops are critical to a successful Agile team, and that you want that team to be cross-functional, to have as much knowledge as possible in that. And right, you're going to start developing software, and for the most part, software development doesn't really end. Like occasionally you have shipping, you have milestones, right? And you have times that projects get shut down. But for the most part, you're just developing new features. And right, here we go. We can see this, and we have the Agile team produces features, and it keeps producing features. The users give us feedback. And again, we can kind of zoom out a little bit. And this maybe we have prioritization of the backlog. We have internal rejection inside the team. The number of features that you produce, maybe we have some sickness that reduces the number of features that's coming in. But we can look at this and we can again think through, it's a structure of things connected by relationships that produce behaviors. And so we can think of the Agile team as a thing. Of course, the Agile team of itself is a social system. There's social interactions in there. The users themselves are interacting, perhaps, and producing feedback within themselves. But this concept of continuously developing, continuously moving along is this system that allows in a nonlinear fashion for us to look at the world around us and understand these relationships a little bit better to be able to understand systems. And so here we go. 3 keys, my favorite 3 keys to understanding systems. You ready? All righty. So the first one is right versus wrong. Now this is a classic question. Humans love to be moralistic. I'm right, you're wrong. We do this with political setups, at the geopolitical level. We do it at the local level in political setups. And we've been doing it in technology, right, for a long time. And sometimes we forget about the battles as to whether who was right and who was wrong. And sometimes they continue on in a religious fashion. You thought I was going crazy when I put politics up there. Now we have religion. But this whole concept of right versus wrong, when we're talking about systems, this is a wrong framework to think about systems in. And I would say that systems, one of the keys to understanding systems and the keys to especially collaborating on systems is this key, getting rid of right versus wrong, because it's really hard when you're right and I'm wrong to come to some larger idea. We can instead think about usefulness, right? That's what Thomas, the tank engine, always wants to be. He wants to be really useful. And that's what we want our models to be, is really useful. And because if I have a useful model and you have a useful model, then we can see maybe they're useful in the same way, but maybe they're useful in different ways. And that by combining those 2 models, we get a more useful model. Because reality is every model that we go through is wrong. Every single one is wrong because it's a model, right? It's not the real thing. The reason that we have models in physics is so that we can predict things, but we can't predict things perfectly. So we have these useful models that we have in order to help us understand the systems that we're working in. So it's very difficult, I think, in some ways, to get over right versus wrong. Humans are very much, especially in our Western culture, we think a lot about right versus wrong. But yet, we need to leave that to the side as we're thinking about these models, because it's not a useful paradigm to think about our models in. Another key as we're looking into models is as whether or not we're creating a model or whether we're discovering a system that's already there. So if we're trying to create a new system, right, that's one thing that can happen. But if most of the time, we're discovering a system that either used to be there or is still ongoing. Right? And this again, is a technological thing that's been happening since the early days. Hollerith with IBM, with the Census Bureau. He wasn't really changing how the Census Bureau or how Social Security worked. He was merely building into the system that they already had. And other technological groups, such as Xerox PARC, right? This is the most famous one, I think, for actually creating entire new systems. But either way, whether you're creating a system or discovering a system that's there, that one system, of course, interacts with other systems. Anytime you create a system, it's going to interact with other systems. And that leads to very interesting interactions and interesting behaviors. And if our models are useful enough, we can predict, or at least we can try to understand those behaviors and how we interact with them. And then our third key, temporary assumptions. So this is probably the most common place I personally find this useful. As a consultant, I end up going into a lot of old code bases. This is a fairly regular thing. And as you go into a code base, you're attempting to understand what on earth does this thing do, right? And so maybe as you're going through, instead of just trying to understand it piece by piece, I suggest that another way, in a way that's useful as far as creating your models goes, is to say, well, let's assume that this part over here does this. I don't know that it does this, but I think it might. And continuing on and doing that iterative work where you're like, okay, well, I found something else out that supports that thing does what I thought it did. So I'm going to, have that's a little bit stronger of a belief now and keep going. And if I find some evidence that breaks it down, maybe I'll go back and actually find out what that thing does, right? I was wrong, and that's okay. And that's, again, this concept of right versus wrong. You're always wrong, but how useful is that assumption? And so instead of strong opinions weakly held, I suggest weak opinions weakly held when it comes to models and when it comes to understanding systems, because you're always going to be understanding. And it's just a matter of how much can you understand, how much of the behaviors do you understand why things are happening. And it's kind of this fuzzy picture, right? And over time, right there, it's going to resolve into not necessarily perfect, but better. But you see, like all these big splotches, right? You don't know what's in there. You don't know all these pixels and what they're actually doing. But you don't necessarily care. You don't have to care because you can see, hey, there's yellow over there, and there's pink over here. And oh, look, it's more pink over here. Is slowly, iteratively understanding. And it's difficult to do an animation like this, but I would say that you can like kind of leave the butterfly aside and just investigate the flower for a while. The butterfly can be this big splotch of yellow. It's like, oh, it's something over there. And as you go through and develop these systems, you're kind of understanding piece by piece, maybe fuzzy pieces here, fuzzy pieces there, and attempting to find these connections. So there we go, we have it. We have our three keys, right? Everybody remember what they are? Let's see who remembers. What's number one? Wrong. Oh. Good job. All right, what's number two? Usefulness. Creation versus discovery. What's number three? Temporary assumptions. You're holding that a belief very weakly. Thank you. That's good. So here we go. Here's our very short version of modeling, right? What you actually have to get done. Right, the first thing, right, you're going to look for things. And there are lots of different things in the world. Oftentimes it's people, it's events, it's places where you're storing something. It's a whole subsystem, right? You don't have to investigate the whole subsystem. You can just set that aside. And incentives. We'll come back to that one in a minute. But incentives can be a thing. And so then, right, what's of course next? You're going to look for the relationships. And the relationships are these communications. Generally in a relationship, there's some level of communication, information passing. Something that's interacting between these two things. And, even as programming, right, the most common, HTTP is a common one. These interactions, and we can build up these systems, right? They don't have to be with people. They could be with computers, They can be at the HTTP level. And we use these kind of pieces, maybe you're drawing them out, maybe they're just in your head, and you're saying, can I explain the behaviors that I see from these pieces that I've brought up, these relationships and these things? And because everything is systems all the way down, you're also going to have to pick some boundaries, right? And the boundaries can be in two places. One thing can be like, at some point, you're not going to go all the way down to quantum level, right? Oh, he did this because of there was a quantum effect. That's not quite useful, right? That's going to break our key there. But we also have the boundaries of the outside, right? At some point, your system's going to butt up against other systems. A great story about this is I once was working for a company that sent text messages. Okay, and we sent text messages, and people would reply to those text messages, and we would say, hey, thanks for confirming that appointment, whatever the case may be. And we had drawn a boundary around our customers. We thought that everyone we would send a text message to would be a human, right? We limited it to that, and maybe some of you can see where this is going. But there was another company who also was in the business of sending text messages. And, well, every time they got a text message, they didn't process the contents of the text message. They would just send back a message that said, hey, we don't take text messages. Sorry. And of course, we, if in our human thought, right, with our boundary around our users as humans, anytime we got something that we couldn't process, we would say, I'm sorry, I don't know what you're trying to say. Of course, at some point, one of their phone numbers got into our system, and we sent them a text message. And they said, nope, I don't take text messages. To which we said, what on earth are you trying to say? I don't know. To which they said, nope, we don't take text messages. And so around $5,000 Twilio dollars later, we managed to catch this problem and make sure we included in our boundary that computers were also potential users of our system. In our case, ones we wanted to exclude. We were very humanist in that. So boundary picking is important, right? Because you can make mistakes. You can end up with bugs. And that can happen if you're too narrow or if you're too big, right? If you're trying to take too much into your system, then if we decided that maybe we want to be able to parse 50 different languages, even if our users didn't include speakers of Japanese, we need to support every language. Well, you don't want to do that. That's a lot of wasted time. And so picking those boundaries appropriately are important for not wasting time, but also not having $5,000 Twilio bills. So incentives, we're back to this concept. Incentives matter a lot. And one of the problems, even if you think about, you're thinking about these things, and you're saying, oh, well, incentives are things, so I need to think about some incentives. And so I want you for a second, think about what are some incentives that affect you. Okay? So everyone's got an incentive in their mind. I see it. And now, think about this. How many other people on your team know about that incentive? Now, my guess is it's probably not everybody, at least. And so one of the keys with incentives is that they can be really hidden. Have another story about this one. You get lots of good stories today. So we were working at Carbon 5. We were working with a client, and the client also had another contracting company. And this other contracting company provided junior developers. Nothing wrong with that. They were good people. And as we were working together in an agile way, we were seeing some behaviors that we didn't like, right? And that was that they were having lots and lots of stories in flight. These developers, they would go through and they'd start a story, they'd put up a pull request, and they'd go on to the next one, which was fine, but then they'd kind of leave that pull request. Like, if CI failed, they wouldn't go back to it. If people left comments on it, they wouldn't really go back to it. And we tried using the regular agile ways of fixing this, right? You talk about it in retrospectives, and you say, oh, well, maybe you put some rules into place. We never got there, but we discussed it and said, well, you can't have more than X stories in flight. And those were kind of our way to approach the issue. And even if we talked about it in retrospectives, the behaviors would kind of decrease for a little bit, and then it'd come back. And it was this concept we couldn't explain these behaviors. Like, this doesn't make sense. They're smart people. We like them and all of this. Why are we getting these behaviors that we didn't like? And it wasn't until later on that we found out that they had some incentives we didn't know about. They were being graded. They had their own metrics of how many stories they completed, which is fine, good. Completed stories are a good thing, right? There's nothing wrong necessarily with that, but their definition of completed was when the pull request was put up. And so, of course, like if your job's on the line effectively, as a junior developer, you're not very, secure in your job. If you're being graded on how many pull requests you put up, of course you're not going to worry about old pull requests, even if you want to worry about them, right? You're incentivized to go on and start opening more and more pull requests and not worrying about the old ones because, hey, your metrics look good. So incentives are often kind of one of the hidden pieces of a system and I would say if you can't, understand a behavior in a system that you're seeing, that incentives might be something you want to go poke around at and see if you can't find any that are hidden under there. But they're difficult to find because sometimes even like you don't know your own incentives. So it's a difficult thing to dig for, but it's a critical thing if you want to start understanding the behaviors that you're seeing in the systems that you're dealing with. Time. And we can think about this, right? Tetris, time mattered, right? The first part of the Tetris system, if you think back to that, the first part of the Tetris system, you're doing fine. Everything's okay. And the system at some point changed. It had that pivot point where suddenly you couldn't keep up with the falling blocks anymore. Time also matters in that systems are old, right? The reasons that the systems were set up disappear, right? They're not very well documented. But the decisions that people made on those reasons, they stick around. They're all this legacy stuff that we have to deal with. And if we could just throw it all out, it'd be fine. But if you want to look at it from a systems view, if you want to see that history not as something that just happened because someone made a bad decision. Maybe it did. But generally, people have reasons. They have incentives. Maybe those incentives are bad. Maybe the reasons were bad. But as you go through time, the systems take on that organic capability. They grow, they learn, they change, and you may end up with pieces and parts that aren't needed anymore. But time is another kind of piece to the puzzle as you're modeling. So there we go. That's the very, very short version. So we're going to get into the fun part. This is my favorite part, common system problems. And we've already talked about a few in the stories, but I just love problems. I'm a bit of a debugger in life as well as my code. And so these are things that I've found come up again and again in a system, where problems that you're going to have again and again, they're just always going to show up. So this is a great way to kind of get some of that pattern matching in your head maybe of what to look for in a system. So we've got delayed feedback. How many times have you started a story, right? In your agile way, you have this nice, beautifully pointed story, and you do all the work. You do the pull request, you send it off to acceptance, it's all done, and you're like, I'm going to go work on the next story. And the next story is kind of based on that first one. And so you go on and you do a great job, great agile, you make sure your commit messages are beautiful, everything is perfect. It's going great. You're shipping code out the wazoo. And so you send that one off to acceptance and you keep moving on. And you get about 5 stories down, and finally someone from acceptance comes back and says, there was a problem with that first story you sent us, and it needs to change entirely. And suddenly all that other work that you did is not necessarily thrown out the window, but it's all got to be redone. All those beautiful commit messages going to waste. It's sad. And so Agile, right, this is one of the kind of the core tenets of Agile, is that you want to keep those feedback loops short. Another place that you've experienced delayed feedback is how many people played like a first-person shooter before? And you get a little bit of lag going as you're playing the game, and your headshot doesn't hit, and their headshot does, because you're standing there doing nothing. That's that lag, that delayed feedback. It has, in the case of the game, right, it has dire consequences for your avatar. But it's slower in real life, generally. Hopefully your delayed feedback, I don't think anyone's working on any autonomous cars here right now, so your delayed feedback loops can be a little bit slower probably. But that's a problem that is very common, and it tends to disconnect your cause and effect, right? The longer you get, the harder it is to see where's this feedback coming from. So it's one of those common things you can start looking for in a system, because you've always got this feedback. So it's a nice thing to kind of keep track of. Another thing you always have in every system, I know you don't think your system's special, but it has some limits. So in Agile, right, one of the most common ways we talk about this in Agile is the concept of blocked. I'm blocked. Today in stand-up, I'm blocked. I can't do anything until my computer gets fixed. Completely blocked. But limits aren't just about being blocked. They happen in every system. And we talk about these as bottlenecks, right? And if you don't think you have any bottlenecks, you're wrong. I know I said useful, but you're just wrong in this case. That your bottlenecks, maybe they don't necessarily affect what you're currently trying to do, but they're making something slower. Maybe it's that you have too many people. Maybe it's that you aren't getting enough requests for features to actually get anything done, right? If corporate is not asking for a feature from your group, there's nothing to do. The limit's not your group necessarily. The limit maybe is outside your system, or you need to expand your boundaries of your system to understand it. But there's always going to be a limit. And so you should kind of look for and try to understand what are your current limits. And then keep track of them, because as maybe you get rid of one limit, right? The rule is there's always a limit. So if you get rid of a limit, that means there's just a different one to go find. And so here we go. Here's the limit we have here. The limit of my Tetris playing ability stops about right there. And I'm no longer a good Tetris player after about that point. Ooh. So if you're looking for problems, you're probably looking to change a system. But systems are resilient. They don't tend to change much. And my favorite example of this is when you think about when, MoviePass or another big player comes in to try to change an industry. And think about the number of dollars it takes to change that entrenched system. But if you put enough of that work in, you put enough of that money in, you put all that together, systems tend to be very resilient until they start getting brittle, and then suddenly they aren't. And it tends to happen very quickly as things go from being resilient to just switching entirely to another system. You can think about this as maybe a dam, right? The water fills up behind the dam, nothing's happening, right? But eventually, the water is going to broach that dam. You have that threshold that it has to pass, and then suddenly downstream is getting a lot wetter than it used to be. Also, as you're changing, though, you can end up with some unintended side effects. And this I think, is a very common thing we see in our world today. You think about the side effects of a lot of technological innovations, right? We think about, Uber and Lyft and the changes that they've made in transportation, and the perhaps unintended side effect that more cars are on the road. The drastic unintended side effects of social media, right? These are systems that people are building And they're like, yay, let's have everybody be able to respond to everybody. Nobody's going to be mean. It'll be all happy. It's wonderful. And it can also be like small, right? So I was once working with a college. The college had a problem. They wanted to make their application process better. Their application process just filling out the online application took about an hour for people to do, and it was a long time, and so not many people did it. So I was like, oh, we could fix this, and we went through, changed the system, built a whole new application flow, and got it down to about 15 minutes. That was great. Hey, massive improvement in time to fill out. And as we expected, more people filled out the application. Unfortunately, the models for how many people they expected to enroll were based on historical models that were no longer valid. And in this case, the unintended side effect was the administration, like the president, was like, we're going to have so many more people come into our college this year. And of course, that didn't actually happen, right? The number of people changed a little bit, but it wasn't going to, even if we had a tripling of our applicants, but we did not have a tripling of our enrollees. That was a slightly unintended side effect there. There you go. We've got these common system problems that hopefully, and this is a thing you can do with systems, right? As you're thinking about these, you're starting to pattern match. You're starting to see, instead of a structure of things connected by relationships that produces behaviors, you're starting to actually see, oh, there's a system, and that's a system. And maybe you're just going down the street and you're like, oh, look, there's a sewer. That's a system. That goes there, and then it goes there. It goes to the wastewater treatment plant, or it doesn't go to the wastewater treatment plant. That's bad. And that's how, right, these are the systems around us. And as you start to see these systems in your work, in your play, in your life, that you start to see more of them. And hopefully you'll start to see more of them. And hopefully this will give you some starting point or help you along the way to seeing these systems around you. So we've got some more resources here. Lots of great resources. If you look for systems thinking or general systems theory, you can look up a lot of good resources. I will post these in the chat of Slack at least, and probably on the meetup as well. And I suggest looking at How It Works in the Home by Walt Disney. It really is a fun book with lots of great things, how things work. So thank you very much, and I think we got time for some questions.
Before I open the floor to questions, just a quick reminder, last chance to put yourself on the raffle for the IntelliJ license if you have not. I'll stick the sign-up sheet over here, and if there are any questions, we can make rounds.
In the front.
I have a few that are relevant, but one that's not relevant that I'm really curious about is what font are you using?
What font am I using? That's
really
a great
good.
question. This is Ubuntu, actually. It's Ubuntu's font.
All right, any other questions?
All right, well, thank you all for coming out.
Let's go and see who our lucky winner today is. I have number 11 on here. So Jeremy Owens. The license is back there. We'll hand it to you. So, congratulations.